Hello, everyone, and welcome to another Jakarta Tech Talk. My name is Serena, and joining us today is Fabio and Gabriel, who will be presenting on the topic of preventing neonatal brain injury, building a resilient, predictive platform with Jakarta EE and MicroProfile. If you have any questions for Fabio and Gabriel as we move through today's presentation, feel free to ask them in the chat or use the Ask a Questions tab. Without any further delay, Fabio, Gabriel, over to you.
Thank you, Serena.
Thank you, Serena. We're really excited to be here. We'll start just sharing our screen, so just give me 1 sec. Just 1 sec. Please just confirm that you can see our screen, please.
Yes.
All right.
Okay. Thank you, Serena. Hello, everyone. My name is Fabio. I am the CTO at PBSF. I've built my career mainly in the financial service and telecom industries. I now work in healthcare. I'm one of the founders of SoulJava. I've been working with Java, Java EE, and now Jakarta EE since the early days. So many thanks to Eclipse Foundation for this opportunity. Today, we are excited to present a special project we've been working on. Our focus today is edge computing. But before diving into technical details, it's important to provide some context. To do that, let me introduce not only a doctor, but also the founder and president of PBSF, Dr. Gabriel Variani. In addition to leading the company, Dr. Variani is the medical director of the neurological neonatal ICU at Santa Casa of São Paulo, and the president-elect of the Newborn Brain Society. Now, I will hand it over to Gabriel. Please.
All right, then. So in first place, I must say that we're really, really excited to be here today. And the idea is to showcase how we're actually using this beautiful technology to actually help babies thrive and help babies preventing neurological impairment. And I would like to start this presentation actually with a true history of a mother called Natasha and her son called Bento. Natasha was pregnant for the very first time, and she was expecting the happiest day of her life would be when Bento would be born. But actually, when Bento was born, he couldn't cry, he couldn't breathe. And actually, he had a 37-minute cardiac arrest in the very first day of her life. And of his life. And the happiest day of Natasha's life was turning into a tragedy where Bento actually had a really high risk of death. And if he survived, he would have really high risk of cerebral palsy, blindness, or deafness. I'm telling you a single story, but the truth is that every single year, over 10 million infants will have a really high risk for brain injury worldwide. And the economic lifetime cost for each child with disability could reach up to $4 million US. And basically, where comes all this important comparison? Where comes this important burden and impact? And basically from different fronts, but one of the most easy to visualize is the different compared needs in care. When we talk about a children without disabilities, it's much more simple to take care of these children when in comparison with children with severe disabilities, with multidisciplinary approach, special medication, recurrent surgeries, ICU admissions. And in the end of the day, we truly like to brainstorm actually who loses when a child has a severe brain injury. And basically everyone loses, including the patients, of course, with higher mortality, brain injury, but also the hospitals with worse outcomes and high risk for litigation, the health system itself with inefficiency, social security with fewer taxpayers and higher cost of aid, the government itself with high infant mortality rates and less productivity. But in the end of the day, the truth is that every single person loses when fewer children can read, learn, or contribute. And Understanding this scenario, actually, the neonatology field has evolved a lot. And when we talk about the evolution of neonatal neurocritical care, we know that actually the emphasis now directs not only about survival, but actually about quality of life. And this focus actually led to the creation of what we call neonatal neurocritical care units, providing strategies to reduce the risk of brain injury through standardized clinical protocols, the use of specific methodologies, including brain monitoring, which we'll be talking today, lots of education and training. And specifically focusing on brain monitoring, this is truly, truly important for babies at high risk. And here we're just gonna exemplify one reason why. So basically we know that when we are babies, the neonate population has the highest risk and highest incidence of seizures. The higher the number of seizures, the higher the seizure burden, the greater is the risk for permanent injury. The vast majority of seizures in neonates have no clinical manifestation. We're talking about 80 to 90% of cases when a baby is having a seizure. It's completely subclinical, and many babies have non-specific movements that people think they're seizures, but they actually are not. So they're mistakenly confused with seizures, and these babies are giving inappropriate medication in those cases. And properly treating seizures reduces the risk of permanent brain injury on such population. Just to make sure everyone understand and exemplify, we're going to show a case of a baby that was born really well, was in the normal nursery with his mother, and he started doing abnormal movements. This baby was admitted in the ICU, and here you can see the EEG of this baby, and you can see this repetitive pattern lasting for more than 10 seconds. And I say this is a seizure that we can see on the EEG, but I want you to focus on the video image of the baby. And if you pay close attention at the left arm, at the left leg, you're doing this repetitive, this clonic movements that even if we're not doing the EEG, most of the clinical team at the NICU would say, no, this is likely to be a seizure. So this baby received anti-seizure medication, and then we follow for 15 minutes after receiving the anticonvulsant. And here you can see the EEG is very, very, very similar, and this baby is having a new seizure. But as you can see now on the video, the baby is just breathing. He's not moving a single finger. He's not blinking. It's absolutely impossible to know if this baby is having a seizure, yes or not. Otherwise, we are doing the brain monitoring for this baby. And by understanding this very delicate scenario, we wanted to improve neurocritical care education, promote homogeneity of care. We started this digital health project entitled Protecting Brains and Saving Futures. And we implemented this in several NICUs across Brazil, over 50 right now. And the big idea here was actually to develop our solution we call a software plus healthcare as a service solution, in which we are combining multimodal monitoring, telehealth, consultation, AI, and even immersive reality to bring adequate assistance to a large number of babies, ranging from private to public centers here in São Paulo to centers even near the Amazon. So basically what we're doing, we are streaming all data from existing monitors from thousands of babies, and we're bringing all that data from those babies and displaying into proprietary software that we can do multimodal monitoring and using AI. And then we are empowering the physicians, the team at the bedside, to do more precise diagnosis of brain injury. And the system was quite interesting, and we're all already able to actually previously detect life-threatening events up to 8 hours in advance. And it's basically using the best of technology to bring a happy ending for these stories. And being that introduction on, now I'll allow Fabio to actually explain a little bit more what exactly you are doing to provide and to improve the quality of care of those babies here in our country.
Thank you, Gabriel. Now, the medical use case is very clear, highlighting the benefits for families, healthcare providers, and society as a whole. But from a technical perspective, how did you build a solution that meets all these requirements? What the key challenges did you face along the way? Our first challenge was integrate diverse medical devices into our system to collect data. This device uses different physical interface, USB, RS-232, RJ45 cables, and diverse communication protocols, including HL7 for vital signs monitors, LSL for EEG real-time signal stream, Medbus, an ASCII-based protocol commonly found in infusion pumps and ventilators, and sometimes proprietary protocols. The volume and frequency of data transmission can differ significantly. For instance, some devices stream data at 200 Hz, transmitting hundreds of data points per second, which introduce challenges for integration and real-time processing. Our second challenge was to shift some processing tasks from the cloud to the edge, not only to reduce cloud costs, but primarily to accelerate the detection of critical events. In this time-sensitive scenario, every minute matters and can impact clinical outcomes. Instead of just collecting data at the bedside, our edge device now processes it locally. This approach not only reduces latency, but also shields us from potential problems such as unstable internet connections or cloud slowdowns. At the same time, the cloud complements the setup with scalable AI models, centralized data aggregation, and long-term analytics, enabling pattern detection, crisp predictions, and continuous algorithms improvements to increase accuracy and enhance the quality of care. The strategic balance between edge processing and cloud capabilities has profoundly shaped the project and has defined our entire architecture. While edge compute enables near real-time case detection, it also introduces technical challenges that exceed the capabilities of our legacy system. To address these challenges, we evaluated several commercial off-the-shelf solutions and cloud provider packages to edge to speed up time to market, but none meet our requirements. So we define a clear set of requirements for developing our new solution, putting focus on performance, throughput, enterprise-grade tooling, and features that work well in both cloud and edge environments. Dependency injection in any form was a fundamental requirement. After testing several languages and frameworks, particularly for edge computing, one platform emerged as the best solution: the Java ecosystem, with Jakarta EE and Eclipse MicroProfile consistently leads across all evaluated criteria. The diagram illustrates the high level of architecture of our multimodal platform and its integration with the Neonatal ICU. At the bedside, multiple medical devices, including monitors, ventilators, and EEG systems, continuously feed time series data into our edge platform. Local processing identifies crisis events in near real time, critical events in near real time, while the data is also sent to the cloud through a unified pipeline orchestrated by a software stack built on Jakarta EE and MicroProfile. In the cloud, this data enables large-scale analytics and centralized monitoring, powered by Kubernetes-hosted microprofile services. The same Jakarta EE and microprofile stack also expose APIs for integration with external systems. At the core of our platform are Eclipse MicroProfile and its core specifications, but to play a pivotal role at the edge. CGI Lite ensures modular, maintainable code with safe and lightweight dependency injection, and fault tolerance provides resilience in an unstable and resource-constrained environment. In the cloud, you leverage Jakarta EE APIs like JAX-RS, JPA, and WebSockets. Together, these technologies enable a seamless end-to-end architecture from bedside to cloud that remains fully portable across environments and free from vendor lock-in. In addition, we use Eclipse Temurin as our JVM and Quarkus as a microprofile runtime. We store data using InfluxDB and MySQL. On the front end, use React For edge orchestration using micro Kubernetes, a lightweight Kubernetes distribution designed for edge environments, which enable us to remotely deploy and manage devices efficiently. This stack gave us a solid foundation for cloud and edge compute, but the hardest part was still ahead. How to build an unstoppable machine at the edge. Unlike the cloud, edge environments are physically exposed. Users interact directly with the hardware, leading to frequent disconnections. In the ICU, the situation can quickly become chaotic. Bedside teams move patients, adjust settings, unplug cables, or connect new device, all under intense pressure. There is no room for error and no time to restart the system. So, how do you keep everything running? We tackle these challenges using microprofile fault tolerance, a flexible, easy-to-use annotation-based specification for build resilient applications. It supports patterns like retries, timeouts, fallbacks, and circuit breakers. We apply it in an innovative way to ensure continuous operation, even when medical devices become disconnected. In this example, the circuit breaker starts closed, allowing normal data collection. If 5 out of 10 calls fail, based on request volume threshold equals 10 and failure ratio equals 0.5, that means 50%, the circuit opens for 6 seconds, as defined by delay, then moves to a half open state. If 4 calls succeed, as defined by success threshold, it closes again. When the circuit is open or a 5-second timeout occurs, as defined by timeout annotation, an alternative fallback method is called, and the system keeps running in a controlled way, despite some degradation. Other devices remain unaffected, and monitoring continues without restarts. Now, let's move to a quick demo about this implementation.
So we must remind you that the neonatal ICU is a highly complex environment where life-changing decisions are made constantly. So actually there is no room for error or delays. And therefore, our system must be extremely resilient. In the event of an error, the solution should be as fast and simple as possible. And considering that the NICU is filled with wires and cables, for instance, we have adapted our system so that if there is any disconnection or fail to capture the data, the issue can be resolved quickly by simply disconnecting and reconnecting cable to our system.
So, you are applying the original concept of circuit breaker designed to protect electrical systems in an analogous way to handle device cable and device disconnections. Even better, we are applying the same microprofile annotations commonly used in cloud-based microservices now at the edge. Created to prevent cascading failures in distributed systems, these patterns also ensure resilience when devices go offline. No restarts, no service disruption. There is no need to reinvent the wheel. We simply apply proven patterns in a new context. In addition to providing fault tolerance and isolating failures, we use circuit breakers to trigger corrective actions when necessary. As demonstrated at the end of the video, the circuit breakers and fallback methods are integrated with our monitor system, Zabbix, through CDI, enabling real-time tracking of every connection and disconnection event. When a circuit opens, a fallback method is invoked, attempts to restore the connection, and sends a critical alert to Zabbix, notifying the infrastructure team. Encapsulate monitoring logic in CDI inject classes, decoupling infrastructure code from the core business logic. This keeps the system vendor neutral and needs to evolve. At the core, this design is CDI. And CDI is the backbone of our platform, powering repositories, factories, collectors, and data processors. with type-safe, context-aware dependency injection, scoped lifecycle management and annotations like application scoped, injected, post-construct, and pre-destroy provide type-safe injection while ensure reliable initialization and cleanup of medical device. This aligns with dependency inversion principle, reduces boilerplate, and enhances modularity and testability. Beyond injection, CGI provides powerful patterns for building modular and adaptable systems. Event-based observers enable loosely coupled communications, allowing producers and consumers to remain fully decoupled. And interceptors offer a clean way to address cross-cutting concerns like logging and security. Among CGI's runtime flexibility features, Instance G interface enables dynamic type-safe injection of beans at runtime. Leveraging this, we implement a factor that provides medical device instances based on each hospital's configuration. The select device method shown on the right invokes the select method on the instance using an annotation literal to dynamically specify the qualifier at runtime, ensuring the correct medical device implementation is selected and returned. This approach provides a robust mechanism for adapting behavior at runtime. This is the power and beauty of combining these technologies. We benefit from 25 years of enterprise Java maturity. On top of that, you rely on MicroProfile, a lightweight framework that, together with Jakarta EE, has evolved to meet the demands of modern cloud-native applications. This results runtimes that deliver consistent performance, whether in the cloud or at the edge. At the same time, we benefit from over 30 years of continuous evolution of the Java platform, which provides a stable, high-performance, and innovative foundation. These advancements include features such as lambdas, strings, records, and virtual threads, and beyond. And the first and most important modern Java feature we rely on is virtual threads. They are ideal of our application, which requires high throughput and allow us to scale up to millions of concurrent threads per JVM if you need, with minimal overhead for creation and scheduling. Unlike traditional platform threads, virtual threads are not mapped one-to-one to OS threads. Instead, they follow a one-to-one model where many virtual threads share and are scheduled on a small pool of carrier threads, managed by a dedicated fork join pool. This architecture drastically reduces context switches and system calls, making it much more efficient, especially for a device or cloud service handling thousands of concurrent threads. In our system, each device data collector runs as a virtual thread, ensuring high scalability and efficient resource usage. Virtual threads optimize throughput for most communications, but some medical devices act as TCP clients pushing data to a central server. This changes the way we read data. We need to wait for the message and not get it. We address this by decoupling the reception and processing of a message into separate threads, following the producer-consumer pattern. We use interfaces such and classes from Java Util concurrent from Java 5 to manage blocking queues and eliminate the need for manual synchronization. This approach enables safe data exchange between threads by decoupling producers and consumers through asynchronous buffering, fully compatible with virtual threads. This spares us from building critical infrastructure from scratch, reducing errors and increasing reliability. To enable us to efficiently handle non-blocking workloads with high throughput, while still allowing for safe blocking when necessary. And Java records reduce boilerplate code by automatically generating methods such as equals, hashcode, and toString, and they are designed with final and private fields. But for us, the main benefits is that they enable a consistent modeling of mutable data. By enforcing mutability, records reduce concurrency issues, eliminate the need for explicit synchronization, synchronized blocks, and consequently improve performance. And records work well as value objects in domain-driven design and help us model our neuro, pediatric, and neonatal software domains. The compact constructor allows for immediate validation, ensure that objects are created in a valid state. Complex business logic resides in domain services, while records remain simple. This promotes separation of concerns and maintainability by keeping the focus on data representation. Using pattern matching switch statements improves code clarity and safety, eliminates the need for casts after instance of checks, and provides null safety by default. The arrow syntax removes the need for break, making code cleaner and less error-prone. Vanguards allow developers to add conditions to each case, making the code clearer and more precise. Works with sealed class and records, not just constants. These features are especially useful for parsing diverse data formats from medical device. In returning to enterprise features, MicroProfile REST client simplifies service integration by allowing us to define type-safe Java interface to call REST services without manual HTTP code, fully integrated with the ecosystem. It supports config-based URIs, fault tolerance, metrics out of the box. REST clients can be injected, mocked, and tested easily, promoting modular and secure code. They support both sync and async calls with minimal configuration. Overall, REST clients makes it easier to connect services with less code and more reliability. In complement to these features, we leverage security REST service driven by JAX RS, Jakarta Security, and JSON Web Token in the cloud. We also use JPA for database integration. These APIs combined with Kubernetes and MicroProfile Health ensure security, scalability, and maintainability through a modular cloud-native design. Building on this foundation, we have integrating LangChain4j, the standard orchestration for LLMs in Java, enabling this capability in our system. This includes retrieved augment generation, allowing the systems to access clinical protocols, documentation, databases directly from natural language prompts. As a result, medical workflows benefit from faster, context-aware access to critical knowledge, improving operational efficiency and clinical decision support. Let's jump into a quick demo to see this in action.
So, yes. So before running the video, I just would like to say that actually homogeneity of care is certainly one of the largest challenges in neonatology, and therefore we have actually trained a large language model to assist logged users to have quick access to that information and assertive treatments as well. So let's see the demo. Just a second.
Hey, David Guardian, please let me know what are the patients who had seizures in the last 24 hours.
Newborns with seizure activity. Leia Organa Ray, Shmi Skywalker, Jin Urso, Asajj Ventress.
David Guardian, please let me know what is the diagnosis of baby Skywalker.
Diagnosis of baby Skywalker, seizure activity.
David Guardian, baby Skywalker was diagnosed with seizures. Can you please let me know what is the treatment and what is the dose?
Based on neonatal seizure protocols, treatment should begin after confirmation via clinical signs or EEG. The first-line medication is phenobarbital loading dose 20 milligrams per kilogram IV, repeatable up to 40 milligrams per kilogram total. Maintenance dose is 3 to 4 milligrams per kilogram per day. If seizures persist, levetiracetam may be used. 20 milligrams per kilogram IV initial dose up to 60 milligrams per kilogram per day. Other options include phenytoin, midazolam, or lidocaine, depending on clinical condition. Continuous EEG monitoring for at least 24 hours is recommended.
Hey, babe Gordon, please let me know what are the babies with extreme prematurity that are being monitored today.
Extreme premature, Leia Organa.
In addition, use LLMs to retrieve protocols and clinical data. Use AI and real-time correlations to detect critical events. You are also developing neural networks and computer vision techniques to improve accuracy and accelerate clinical response. Once a critical event is detected, our monitoring center is alerted in real time, ensuring the medical team is notified without delay. However, a crucial element remains: performance and resource consumption. The legacy system used 20% of CPU just to push raw data to the cloud. After migrating to Java and Jakarta EE and MicroProfile, the number dropped to 1.5%. Yes, 1.5%. With Java 24, the CPU usage dropped to just 1.1%. Same workload, just a JVM upgrade. Performance was improved by around 50%. However, we didn't just focus on performance gains. The new stack also introduced first level of crash detection, fault tolerance, and real-time monitoring, while reducing CPU usage by over 90% and improved throughput and performance by 50%. Performance, throughput speak for themselves. With Java, Jakarta EE, and MicroProfile, the new version isn't just faster, it's much more efficient. Where the outcomes for our architecture: high performance with minimal resource usage, ideal for edge device and cost-effective cloud deployments. Edge resilience powered by microprofile fault tolerance. Modern Java features deliver clean, thread-safe, and high concurrence code, improving productivity and performance. Modular and scalable architecture ensures low coupling and clear separation of concerns. These features accelerate onboarding, simplifies maintenance through well-defined patterns and standards. Beside the architecture, this stack brings many benefits. Jakarta EE and MicroProfile offer more than just tools. They provide a stable and flexible foundation with long-term value. Open standards and modular design prevent vendor lock-in and support modernization without disruption. Driven by a collaborative community, the platform continues to evolve to ensure interoperability and sustainability. Designed for enterprise Java, cloud-native applications, and microservices, and now proven at the edge, it integrates well with Kubernetes, CI/CD pipelines, and observability tools. Together, these technologies provide a foundation that protects both corporate investments and individual learning paths. This is especially important for our professional journey. In this project, for instance, we actively use features available since the earliest version of Enterprise Java, such as container-managed annotations like post-construct and pre-destroy. While tools and paradigms continue to evolve and technology changes, the core Jakarta APIs, such as servlets, CGI, JPA, and JAX-RS, remain evolving, powerful, and widely supported. This platform blends maturity and innovation to meet today's demands and empower professionals with a sustainable path to long-term growth and lasting relevance, thanks to Eclipse Foundation and the Java community. Now, Gabriel will show you how you are applying this technology to scale our solution worldwide.
Well, Fabio, thank you. Thank you so much for leading this technology into our main reason. And right now, I'd like to show you some of the results, what we're currently applying this in Brazil and even internationally. So basically, this project now is providing assistance to over 50 hospitals in our country. We have also 5 international projects, and we have monitored over 900,000 hours from over 16,000 babies. This project also has several publications, scientific international journals, and we were nominated to several awards nationally and internationally, such as in Microsoft Hackathon and Global Tech Innovator from KPMG. And our solution has been proven so effective that it's now considered the legal standard of care in São Paulo city, which is the largest city in the Southern Hemisphere. And by connecting our solution to existing devices inside the NICU, we truly have a scalable model in which we are decreasing the cost per bed while increasing the number of hospitals and exponentially growing revenue. This project comes together with important partners and collaborations, such as the team and professionals from Stanford University and also from Microsoft. And I truly believe that our uniqueness comes from combining a precise and scalable solution together with medical and technical expertise, the largest database, and IP. And together we'll touch millions of lives. And considering this is a huge challenge, not for Brazil, but actually worldwide, I'd really like to share this quote from Anton Lake, former executive director from UNICEF, where he says, "Somewhere, a boy is being told that he cannot play because he cannot walk, or a girl that she cannot learn because she cannot see. Well, that boy deserves a chance to play, and all will benefit." That's the most true. All would benefit when that grow and our children can read, learn, and contribute. Well, the path forward will be challenged, but you know what? Children do not accept unnecessary limits, neither should we. And considering every single life matters, you may be wondering what happened to Bento, because when he was born, he couldn't cry, he couldn't breathe, and got like a 37-minute cardiac arrest. And after that period, our technology was there, and I will allow Bento to actually say to you what was the outcome of this history. And that's our true reason why. Thank you so much for your attention. It was a great pleasure, and I'm sure we're certainly open for Q&A. Thank you so much.
Thank you, Gabriel and Fabio, for that excellent presentation. I just want to encourage everybody again, if there's any questions, to please put them in the chat or the Ask a Questions tab. I will just quickly take a spin here, make sure everything looks good. Nope. So we don't have any questions in the chat or in the Ask a Questions tab. But with that said, if you do have any questions, you can put them in here, and Fabio and Gabriel can follow up and look at them later on. And also, we do have several other tech talks that are coming up, so I'd like to take this opportunity to invite you guys into the Credcast platform and spend some time in reserving your spot and saving your spot. We have great technologies to share with you. So thank you again, Gabriel, Fabio. Have yourselves all a wonderful day. Much appreciated.
Thank you.
Thank you. Thank you so much.
Bye.
Bye-bye.